Welcome everyone. We are now going to discuss or review some of the concepts that you studied in chemical thermodynamics and in separations regarding the equilibrium between a vapor and a liquid, and is usually summarized or referred to as VLE, vapor-liquid equilibrium. And we have to start with this concept of equilibrium, and it will be germane to this lab to allow our system to reach that equilibrium as close as we can. When we have a mixture in a closed environment, and of course for the sake of simplicity we're going to take a binary mixture, it's made of two components. In the liquid, we will have a certain concentration of one of the components and the complementary concentration on the other component. If we express them in mole fractions, then both mole fractions should add up to 1. So X would be the mole fraction of one component. So let's call this component number 1, and component number 2 would have a mole fraction of 1 minus X. These are mole fractions in the liquid. Now, if the space above does not contain anything at all in an initial ideal situation, eventually some of the molecules that have a higher energy content here, remember the molecules in the liquid don't all have the same energy. Some have higher energy, some have lower. There's a Maxwell-Boltzmann distribution. So one of these is going to, some of the molecules are going to occupy the space, they're going to go out and then come back in, and there will be a rate at which they go out, a rate at which they come in, and once those rates become the same, we have reached an equilibrium. And the same will happen with the molecules of the other species. However, because the melting point and the enthalpy of the two species are different due to their different molecular weight, their different polarity, etc. Those two molecules are not going to be present in the same mole fractions in the gas side or vapor side as they are in the liquid side, unless we are in some very special situation which is called an azeotropic point. Everywhere else, in every other concentration at a particular temperature, the concentration of the vapor for each component will be different from the concentration of the liquid for the same component. So here we have the liquid. Here we have the vapor. And we are going to maintain constant the temperature, and depending on the system in which we are working, we might also maintain constant the pressure, but we cannot maintain both of them constant and then want to have a particular concentration. Conceptually, it's a bit easier to understand how this process happens at a constant temperature. So imagine that instead of imposing the temperature, we allow the pressure to be constant, and then we read at which temperature the equilibrium is reached. This is exactly what we are going to do by using a trick. And that trick is that we're going to open this here, and we're going to allow this to be open to the atmosphere. And then you would say, hey, wait a minute, but all the vapor is going to escape to the atmosphere and air is going to come in and so on. So to prevent that from happening, we're going to place a condenser stream here. So there's going to be cold water coming in here, right? Cold water. It's going to be circulating, and it's going to create a trap so that our molecules that are in a vapor state and are trying to escape get condensed, and we give them an alternate path to return to the liquid. So when they condense, they don't drip there directly, they go kind of through another path and go back. So when we let this system boil for a while or equilibrate, what we do is we're going to need to provide some amount of heat, because here we are removing heat by condensing that. Then we have to replace that heat. So we're going to introduce here a heater. And I'm going to leave this drawing like this for a moment because it's useful to explain the equilibrium, but then I'll make a drawing that's a bit closer to how that apparatus actually looks like. All right, so what we're going to do then is we have fixed the pressure, because now the total pressure is the atmospheric pressure, and we have a particular composition here, and we provide a small amount of heat, just enough to keep it evaporating and condensing again. And if we have it like that, and we take a sample here, we can sample the liquid. And if we sample, when the vapor goes and condenses and comes back, we can, in this path, somehow sample the vapor. We can have a sample there, okay? Now, the same way as the liquid has mole fractions, the vapor also has its own mole fractions. And for convenience, we're going to call them Y instead of X. That way we don't confuse the liquid with the vapor. And component 2 then will be 1 minus Y, because this is a binary system. Remember, we're talking about mole fractions, in this case for the vapor. Now, once we can determine these fractions, we're going to put them into the fundamental thermodynamic expression for equilibrium that you guys are familiar from chemical thermodynamics and separations. This is a law derived from a modification of Raoult's law. Basically, what we are going to say is that the mole fraction of a component in the vapor multiplied by the pressure, and this, remember, according to Dalton's law, is the partial pressure of one component, of, in this case, suppose this could be component 1 or 2, is the partial pressure of that component in the vapor phase. Okay? And we're going to say that that partial pressure of that component in the vapor phase has to be equal to the vapor pressure of the same component in the liquid. And how do we calculate that vapor pressure? Raoult's law says that you multiply the mole fraction of the same component in the liquid by the vapor pressure that this component would have if it was pure at the temperature at which you are working. So once we measure the temperature, we can calculate this by using usually the Antoine equation, which is an equation that predicts vapor pressure. You are all familiar with it from the same course. Now we know that this equality only exists in an ideal system, and therefore to make it real we have to introduce a sort of fudge factor that has the very revered name of activity coefficient, because that way if we say fudge factor people might not believe us. So the activity coefficient also is given a fancy Greek letter gamma, otherwise people would not really believe it. And there is many equations to try to predict this activity coefficient based on the compositions in the liquid. The equation that we are going to use in this particular experience is the Van Laar equation. the gentleman who invented that equation. And it's an equation that has an empirical coefficient, actually two empirical coefficients, that somehow represent the interaction of molecules of kind 1 with molecules of kind 2, and on the other side, the interaction of a molecule of kind 2 with a bunch of molecules of kind 1. So this particular equation can be fit, as I said, with any kind of activity coefficient, but we are particularly going to use the Van Laar coefficient because it's easy to use for systems that have an azeotrope, which is what we're going to try to study here. So the Van Laar equation, in this case, well, I'm going to put here 1 so there's no confusion. It says that the natural logarithm of the activity coefficient is a function of an activity coefficient, an interaction coefficient between molecules type 1 and molecules type 2 multiplied by x2 squared. Now, x2 is this, right? The composition of component 2. So this is equal to x2 and this is x1. Okay? Component 1, mole fraction in the liquid, x1, mole fraction in the liquid, x2. In the case of a binary mixture, they are very easy to calculate from each other. And this is divided by the ratio of these interaction coefficients. And it might be a bit strange to say why there is 2 interaction coefficients. And it's because if you imagine that you take a molecule of component 1 and throw it in a sea of molecules of component 2, the interactions of that molecule are going to be of a certain kind. But if you take one molecule of component number 2 and throw it in a sea of component number 1, it's going to be different. And that's what those two components tend to represent. What happens in the extreme dilution of one component and then the extreme dilution of the other component. And this is multiplied by x1 plus x2. And a symmetric expression to that, sorry, this all goes squared. The symmetric expression to that is that the natural logarithm of gamma 2 is going to be equal to a to 1 x1 squared a to 1 over a1 2 multiplied by x2 plus x1 squared. Now, remember that here in our case, because it's a binary system, we only have one unknown in x, because x2 is always going to be equal to 1 minus x1. So we always have these two expressions are a function of two parameters, which are a12 and a21. These two are parameters characteristic of the substances that you're using within a very broad range of temperatures. They are more or less constant. Whereas these compositions are going to change depending on how much you put of each molecule in the system. And the way we are going to approach this is we're going to fill our system with different initial compositions and let it reach equilibrium. And then we're going to sample the liquid, we're going to sample the vapor, and we're going to try to complete or to fit these equations. As you can see, if this equation was written for our two systems, we could rewrite it in the following way. Y1 multiplied by the pressure, the total pressure, is going to be equal to gamma 1 multiplied by x1 multiplied by P1, and this is at a given temperature. Okay? So this pressure is going to stay constant, but this temperature might change depending on the compositions. And then 1 minus y1 multiplied by P is going to be equal to gamma 2 multiplied by 1 minus x1 multiplied by P2, 0 at a given temperature. And for any pair of data, actually, sorry, not pair, triplet of data that you are going to collect, you're going to collect data that are x1, this y didn't look very good, y1, t. You have these three data, x, y, and t, for different type of mixtures where you start. You're going to then try to fit it to this pair of equation systems. And we will show you how to do that, and you will use a spreadsheet, and you will learn how to do something, if you haven't yet learned, how to do something called nonlinear fitting. Because as you can see, these equations are clearly nonlinear. When you replace this there, this is going to be an exponential function. This is going to be another exponential function, because the Antoine equation is also an exponential function. So you're going to have known values of x, known values of y, known values of temperature. And what are the unknowns? What are we going to try to find? Well, what we're going to try to find are these two interaction parameters of the Van Laar equation. And we want to see how well this equation is going to describe the data that you are going to collect. The way, generically speaking, that this is going to happen is that you are going to plot in a diagram the values of the mole fraction of the liquid, the mole fraction of the vapor, and its corresponding temperatures. So we could have, for example, that in the system that we are using, if this is the composition of the most volatile component, which is the usual convention that we use, if we have a mixture of isopropanol and water, then the most volatile component is the isopropanol. We give it the number 1. Water is the least volatile component. We give it the number 2. And what we know is that if this is 0 isopropanol, that is water, and the boiling point at atmospheric pressure is going to be 100 degrees Celsius. Boiling point of isopropanol, on the other hand, if we had a mole fraction of 1, is going to be, let's say, 82.5 degrees C. That's the theoretical boiling point. So in a perfect system or ideal system where gamma 1 and gamma 2 would always be equal to 1, if it was an ideal system, what we would end up having for equilibrium would be something that would look more or less like this. This would be the ideal one. And what it means is that if you take a particular composition of the liquid at a particular temperature, that's going to be in equilibrium with a particular composition of the vapor. Here we would have, let's say, 0.4, and maybe here's 0.85 at a temperature that is between 100 and 82, suppose 90. That's how we read this kind of ideal diagram. The reality, however, is somewhat different, and you are going to find that this system has an azeotrope. Now, there's two kinds of azeotropes. There is high boiling point azeotropes, and in this case you end up finding situations like this one, and this is going to be a temperature that is going to be larger than 100 degrees Celsius. That's if you had that kind of high boiling azeotrope. Or you end up having low boiling point azeotropes, which would look something like that, in which what you get is a boiling point in the minimum, in which the temperature is lower, in this case than 82.5 degrees Celsius. Right? The characteristic of an azeotrope point is that the composition, the mole fraction of the liquid here and the mole fraction of the vapor is the same. You go up here from the liquid, you go down there to the same place for the vapor. In this example here, you would have gone up for the liquid and gone down for the vapor. And the azeotrope composition will be linked to a particular azeotrope temperature. In one side of the azeotrope, you will have compositions of the liquid that are smaller than the composition of the vapor, whereas in the other side of the azeotrope, the opposite will be true. If it's a minimum boiling point azeotrope, then the left side will behave as an ideal system, the right side as the inverse of an ideal system. If you have a high point azeotrope, then it will be the opposite. So what you will determine with your experiment here is whether the isopropanol water system belongs to this minimum azeotrope or maximum azeotrope. And then you are going to use the values that you got, the triplet values of vapor composition, liquid composition, and temperature to determine the interaction parameters of Van Laar by trying to fit these equations to your data. This is the theory behind the experiment. Now there's a number of experimental details that you have to be very careful about. The actual setup of the system is inside a dwarf flask which has some vacuum to help maintain the temperature constant. Right? So here's the system there. There's some vacuum tube, it's made of glass. And here there is a heating element, and this heating element is connected to a variac, which in turn is plugged into the wall. Okay, so this is a variac. And here there is a resistor. And this is full of sand inside a glass tube. The mixture is loaded here so that it covers that glass. And it's very important that it covers it because there is nothing here to turn off this element if it gets too hot. So when it's covered, then the boiling will take away the heat and will keep the temperature of that element moderate. Also, we will add some small boiling pebbles or boiling chips. These are small pieces of material that have a lot of surface in them, and they act as nucleation sites and make it easier for the evaporation to happen in a continuous fashion rather than in sudden coughs. However, you might see this kind of sudden coughs sometime. On the top there will be a condenser, as we explained before. That condenser will have some running water. And this running water must be on at all times. Before you even plug the heater, you have to make sure the cooling water is running. Because you are going to feed this liquid from the top here, another thing that's important is that this has been cooled down if you're going to replace it. So how do we sample this? Well, there's a little tube here where we can take samples of the liquid, and we can also use that to empty it. When it's empty, if this has not been unplugged and cooled down, its temperature is going to start to increase. And if you have a mixture that has lots of isopropanol in it, and you threw it from here, all of a sudden what's going to happen is that's going to absorb heat instantly, it's going to flash up and evaporate. As that happens, this glass will be cooled down almost instantly. It might crack, And if so happens, the isopropanol, now a mixture of vapor and liquid, will be in contact with a very high temperature element, and an explosion may ensue. It has never happened, but is a possible scenario. So please make sure that the element is always cooled down before you apply the next sample. Now there is a switch here to just turn it off. You don't need to move the variac. It's already set to an ice point. Now the condensate that drops through here goes to a little collector that allows you to sample it, to sample the vapor phase whenever you want, right? And you have to remember that when you change samples, some of the old sample gets stuck here, and also some of the initial value before you reach equilibrium. So you might want to drain this before actually sampling. Don't take just the first bit that goes out. Get out some of the material, you take it out, and you can either return it to the system or you can throw it away. The other part that you are going to do here has to do with the calibration of the refractometer. And that is done because we are going to use a refractometer to estimate the concentrations. And that refractometer is going to operate by placing a little drop. I'm not going to go in all the details yet on how to operate it. And we'll do that with the actual refractometer rather than here. But basically you need to place a drop of the liquid on the surface of the refractometer, close the prism of the refractometer, and the refractometer will be at a controlled temperature. So that little droplet will very quickly equilibrate to the temperature of the refractometer. So the temperature at which you're going to read the refractive index is not the same temperature that you read here in this instrument. Remember that. It's just a reference. So what you'll do is you'll take a number of solutions that have been prepared with a known composition. You're going to put them in the refractometer, and you're going to create a calibration curve of refractive index versus composition of isopropanol. The instrument that you're going to use is fitted here with a thermocouple. It's actually a type T thermocouple, and it's connected to a display, a reader, that is going to read the temperature. So you have to make sure that the temperature is stable when you're reading it, and you're going to take sequential 2 or 3 sequential measurements of these compositions until they are also constant. Once you have a constant temperature and constant compositions, you've reached a state of equilibrium. It's not changing anymore in time, and you're going to write down those data. The way you're going to measure these concentrations is by measuring the refractive index. So you have to make sure the refractometer is very clean between measurements, that you are not using the same dropper or whatever it is that you're using, because then you're going to mix solutions, or at least rinse it. And that's it. Now you need to take a few measurements, because otherwise you'll have huge errors. So don't just take one and go do it. You have to take normally 3 or something like that. When we take samples from the boiling point or vapor liquid equilibrium apparatus, one important thing will be to have them, as soon as they're collected, you have to close them. Otherwise, some of your sample might evaporate and you might change the concentrations. So they will be closed, and you are going to use a dropper to take a drop out of it and place it in the refractometer. So these are going to be your 2 main tools. Now make sure the droppers are clean and dry, otherwise you contaminate the current sample with the previous one that you've taken. So this is how a dropper looks, right? And this is the type of tube that we are going to use to store the sample. The instrument that we're going to use to measure the refractive index, and from the refractive index to calculate the mole fraction, is an Abe refractometer. these are extremely sensitive instruments that are designed by using sets of prisms that you can adjust to find the refractive index. So the refractometer now is connected through a set of hoses to this water bath, and the water bath keeps the temperature of the head of the refractometer at 20 degrees. The refractometer opens here like that, very simple to open, no force required, and will close in the same way. There's a tiny gap between the surface of this prism and the one down here, very, very, very small. So all we want to do is place a couple of droplets in here, and then once we close the prism, it will spread the droplet all over the surface. And after we close it, it will very quickly equilibrate to the temperature of the refractometer. So it doesn't really matter at what temperature we pick the sample. All the samples will be read at the temperature of the refractometer, which is now controlled by the bath. So this button here is, this dial here is going to allow you to first find a sharp line through this objective here, or eyepiece, sorry, here. So first thing I'm going to do, I'm going to remove my safety glasses for a moment, because I wear glasses and then I cannot do it if I don't. And then we can bring this light here. Usually we can use a little coin, a quarter or something, to tighten it. See if that works. Yeah, so we have to tighten this because it gets loose as it's been used. Okay, that's good enough. So the light goes into that little window, and then I can first adjust it to find a sharp edge. And once we find that sharp edge, oh, this has moved too much. I need to find it there. Now we can to create a very sharp edge. There, I find it, and that sharp edge will approximately tell you the temperature of the prisms, roughly. So now it's close to 18 degrees, although here the room certainly feels today much warmer. So you're going to find that there's a very sharp line. Once you have that sharp line, then you will try to adjust that sharp line to the crosshairs. So there's a vertical crosshair and there's an X crosshair, and they are aligned. And then when you move this dial, you will be able to move something that looks like a horizon. It will be a little bit darker in the bottom, a little bit brighter in the top, and you can move it up and down. So what you're going to do is move it so that it matches exactly the crosshairs. Once you've done that, then you're going to push a little button here, and then you're going to be able to read on the scale. Now you have to pay attention to the divisions of the scale, otherwise you are liable to read the wrong number. So you see, I've read 4 decimals. Sometimes when it's in between 2 lines, you can estimate half of that. Your eye would allow you to do that. So if it's between 5, 0 and 1, you can say 75 instead of 50, and you would get 1 extra decimal there. Now, it's a good practice that 2 people do this, and 1 person reads and writes, then moves the scale, another person does it again and writes it, and that way we prevent a very common mistake that happens in the lab, which is people are tired and you flip numbers and you're writing 1.335 and you end up writing 1.353. So if 2 people do it independently and they write it, then we reduce the chance of that. You also want to repeat it. So what you do is you open the refractometer, right? You clean the surface very carefully, make sure it's very dry, and then you apply whatever is your next sample. You will apply it again, and then adjust it another time. So now I'm going to adjust it. It has changed a little because probably has warmed up a little. Get the horizon, we push it. And now it's a little bit beyond, it's almost 2 already. 1.3320 now. So it has changed a little bit, perhaps because the temperature has changed a little bit. So this is the the operation of this instrument. And as I mentioned before, it's very important that you don't contaminate between samples, because there's such a tiny amount of sample there that if you end up mixing a little bit of another one, you get a completely different reading. So you have a Kim wipe, don't use the rough tissue there, use only the Kim wipes, and then clean it and put the next sample every time you are going to do it. To provide a calibration between the refractive index that we are going to measure here and the composition, what we are going to do is prepare 7 intermediate compositions. So these are mixtures from A to G there that contain different proportions of isopropanol and water, covering a range approximately between 0.1 and 0.9, although the mixtures are going to be prepared by weight. Then the two extremes are pure isopropanol, which corresponds to a mole fraction of 1, and pure water, which corresponds to a mole fraction of 0. And what you are going to do is prepare those mixtures on this scale by weight. So you're going to add a certain weight of water, you're going to calculate how much you need, then you're going to add a certain weight of isopropanol, so you can prepare something like 200 milliliters or something like that, or 300 milliliters, whatever is in your manual. And you are going to assume that by simply writing the weights, what you have is a very precise gravimetric measurement of the composition. With those weights and the corresponding mole weights, molar weights, and molecular weights, you can find very simply the mole fractions. Once you have those known mole fractions, you are going to make a table of the refractive index versus the mole fraction, and you're going to convert that table in Excel to a calibration function so that you can input the refractive index and output the mole fraction. Now, because you want to have this done in a reproducible manner, you want to make sure you do at least 3 times the measurement. So take this one, put it there, clean it, do the measurement, and take the other one, and so on. So do that 3 times so you have a reliable curve. Since it takes some time for the experiment to equilibrate, you have time to do this more or less simultaneously as you are doing the other part of the lab.
All right, here we are at the vapor-liquid equilibrium setup. Before we begin, we want to go over the safety considerations for this laboratory. As was mentioned in the theory section, we will be working with isopropanol and the vapor thereof, and there is the potential for sparks. Therefore, we will be conducting the entire experiment within the fume hood. Throughout the duration of the experiment, the fume hood must be lowered to the set operating height, with the one exception when we'll be loading the apparatus, which we'll discuss when we actually go to do so. For the purpose of this video, we'll be keeping the fume hood up so that you can see the apparatus unobstructed, but for the duration of the experiment, please keep the fume hood down. Additionally, while in this laboratory, F103, you'll be required to wear gloves, coat, and glasses at all times. The glasses are especially pertinent as the chemicals we are working with are potentially damaging. All right, so the apparatus, we have to the left the refractometer, which will be, the operation will be explained by Dr. Mazzante. We have a variable AC, which will be controlling the power to the heater. For the duration of this experiment, we'll be using it in an on-off fashion. We've adjusted the variable AC to a setting that will be appropriate for the laboratory. In order to turn on the apparatus, you click down until you see the orange light come on, but unless you're ready to run the apparatus and everything is in place, you should make sure at all times the light is off. We'll be quizzing you on this during the lab. Secondly, we have the analytical balance, which is accurate to 1 decimal place. You'll be using this apparatus to determine the concentrations of the mixtures you'll be putting together. We'll have our water bath here. We'll be preheating several of the samples before you place them into the apparatus, as this will reduce the overall time required to complete the laboratory. Finally, we have the apparatus here. Starting from the top, we have the sampling, which you may or may not be able to see at the moment. It is a funnel which will enter the apparatus, which will allow us to put our solution right down to the bottom. Then we have our condenser surrounding our thermocouple. Our T-type thermocouple is connected to our thermocouple reader here. As you can see in the lab, it's about 23 degrees today, very humid. Next, we have our vapor collection area, where we have our vapor collection sample port, which will collect the distilled sample from the condenser, which is how we'll be able to determine the concentration of the vapor. And down here, we'll have our liquid sample, where we'll be able to detect the concentration of the liquid by assessing both the refractive index of both. Finally, our heater comes up to about here. At all times, this must be covered in liquid during operation. It is a packed sand around an electrical output. Again, if this is allowed to cool down or expand too quickly, if the load is too hot, it will crack. And if it cracks, you'll be exposing bare resistance wire to whatever vapor that you're concocting, which is potentially explosive. The operation, once you have everything going, is fairly simple. You'll be adding in your sample up through the top port, and I'll give an example here. Until you've covered the heating element. If you go too far, you can remove some as such by opening the stop port. Now, before you even begin to think of turning on the heating element, you must ensure that the cooling water is on for the duration of the lab. The cooling water switch, located here, you'll be turning on very slowly. It doesn't require much flow of water to remove the small amount of heat that we're providing to the heating element. You'll see this flow of water come in and then exit through here, and you can always double check that there's a steady flow of cooling water exiting the system. Once you have the cooling water exiting the system, you have covered the heating element with the sample that you'll be looking to assess. You can then activate the heating element as indicated by the orange light, and we'll slowly see the temperature of the vapor rise until an equilibrium is established. At which point you'll be able to take samples, again, from the vapor as such. Make sure you clear the lines before you take sample, with the exception of the 2 samples that are required to take immediately and then subsequently. Make sure you read the instructions fully before taking a sample, as these will be very important data points for you to properly characterize both the mixtures and the azeotrope. Now we have a sample of water, pure water, which is boiling at approximately 100 degrees Celsius. As you can see, we've established an equilibrium between the liquid and the vapor section of the apparatus. And the condenser is working. As you can see, there's condensation on the inside of the vessel, leaving our sample port fairly open to the atmosphere, which allows us to maintain our pressure without building up. When taking a sample from our vapor sample port, you notice that there's a little bit of sample from the previous experiment. We will simply remove a little bit of that prior to taking our sample for this vapor. We'll then assess the refractive index of this sample. When writing up the report for this laboratory, make sure you put special emphasis on the calibration curve between the refractive index and the concentration of isopropanol, the TXY diagram, the Van Leer constants, and any deviations from this experiment to what you'd expect to see based upon your known characteristics of isopropanol and water.